of Shahin to speak to us. He's our participant from Iran, and it's very good to have him here for more or less the whole program. So the topic, classification of rough surfaces. Iran certainly has a rough surface. Using Schramm-Loewner evolution.
Thank you. Well, it's both an honor and a pleasure to speak here. I am very thankful for being given this opportunity to participate in this program, which, by the way, I congratulate the organizers. It's a very well organized and good mix of people. I mean, I have not often I participate in meetings where physicists and mathematicians live side by side and no fights happen. So what I'm going to talk about is classification of rough surfaces. It's a physics problem. I always like to have a physics problem in mind to know where I'm going. And the question is, can you in some sense classify the roughness of surfaces? See, if you shut your eye and touch various surfaces, you can tell that they are different. You have a feeling that they are different. But is this a continuum of difference, or is this a disjoint set of differences? This is the question. So the way I'm going to do that, or in fact I'm not going to do it because I don't know whether this classification is possible or not, I'm going to attempt to it, is to use the theory of Schramm-Loewner evolution to assign certain characteristics to rough surfaces. This has been done, assignment of characteristics to rough surfaces has been done before by looking at what is called the roughness exponent. It seems not enough to just assign one exponent. There must be other exponents. There must be a whole set of, or maybe an infinity of exponents to assign to a particular surface. So the effort is to see if we can somehow add to this already existing literature on assignment of exponents to surfaces. So this is the content of my work. I'm not going to present a single result. I'm actually going to give you a review of what I've been doing over the last few years. What I will spend some time on is to explain the theory of Schramm-Loewner evolutions, which was originally developed as a theory of random simple curves with conformally invariant probability distribution over the complex plane. They then were used to describe domain interfaces at a criticality. So you have a critical system such as the Ising model. It spins up, spins down, and they meet somewhere. That domain wall turns out to be a Schramm-Loewner trace. Yes. Then I argue that isoheight lines on rough surfaces can be interpreted as Schramm-Loewner evolutions, and this then may be regarded, if I'm right, then this could be regarded as some evidence of existence of conformal invariance in rough surfaces, and it is a contribution towards classification of affine surfaces. So that would be a surface in 2+1 dimension. That is, you have a surface, and the surface is growing in time. So you have two space and one time. So this is where the evidence stands now. There is good evidence that SLE curves in two-dimensional turbulence exist. Then for the KPZ surface, that is the Carter-Parisi-Zhang equation, forms a surface, and that gives you an SLE surface. This is a computer simulated surface. Edwards-Wilkinson surface is the best studied surface because it has a nice Gaussian distribution, and it is.
Kappa, sorry.
Sorry.
Kappa.
Kappa is a parameter by which I identify which Schramm-Loewner evolution I'm talking about. So if you bear with me a few minutes, I will explain the Schramm-Loewner evolution, and kappa becomes apparent. I'm just giving a complete set of results here. I am in fact not going to present all of these today, just 2 or 3 of them. I will talk about turbulence in detail because it is a little close to your heart of the people here. And I will also tell you about this deposited tungsten oxide surface, which is a physically grown in the lab surface. And I will talk about this most recent result we have, which is on watersheds. And each one of these is related to a different Schramm-Loewner evolution, and these are, so there is a growing body of evidence that Schramm-Loewner evolution can be applied to describe rough surfaces. So this is a large number of work, and I have various collaborators who are named here. So specifically, the problem is this. Somebody in the lab grows a surface, usually by vapor deposition, and some tungsten oxide. This surface comes out. This is an atomic force microscope image of tungsten oxide, which has been digitized. So what I get is this digitized curve, or digitized surface. And I have to now say, what are the characteristics of this surface? The problem is daunting. I mean, when you think about characterizing rough surfaces, the whole set of things that you have to think about is far too large. So obviously, I'm not going to succeed to do it, but just make a headway. I'm going to base myself in a setting where I have some evolution equation describing the surface. That would be the time derivative of some height function, which is related to, which is given by a differential operator acting on H, plus some noise. The noise may be white or color, which would then give me a random surface, a random height over 2 dimensions. Examples are, so you can take the simplest case. We can take the Edwards-Wilkinson surface with a Laplacian as your differential operator, or the Mullins-Herring surface with square of the Laplacian, or the Carter-Parisi-Zhang surface I already mentioned, which has this nonlinear term. So it's possible to have nonlinear terms as well. Now, the question is, do universality classes exist at all? If I am going to succeed, I have to be able to argue that certain surfaces, although they look different, they are somehow the same if you classify them by these exponents. I cannot use yes.
But these equations that you showed, are they in any sense motivated by the real mechanism of growth?
Yes.
They are.
They are. Yes.
It's not just a mathematical device to grow something around.
No. So they are. So obviously the first one, so I can tell you what they are. Obviously the first one is the heat equation. The second one is the equation that controls the growth of a cancerous cell in the surface of a cancerous cell. So it's a very disturbing equation. The third one, in fact, these gentlemen invented that to describe a surface which has hangovers. You know, this sort of has things which go over, like end of a wave.
Hooks.
Hooks, that's right. But it turned out that actually it describes a large number of problems in physics.
All those guys are isotropic in plane because it's only gradient.
Yes.
Square. So no, in isotropic for metallic surfaces it's not the case, and all those guys are local. No non-locality in space.
No non-locality. I have not considered any non-locality. I have, and yes, they are isotropic in surface. There are other symmetries as well. So they have generally the Galilean set of symmetries. So you can rotate and you can boost to a frame with finite velocity. But then this surface does not have a top-down symmetry. So if you change h to minus h, it doesn't go back to itself, whereas the other two do. And that turns out to be a very important factor when you analyze these surfaces, whether the lack of this symmetry is important.
So you're assuming the noise has an average value of 0?
So I'm assuming the noise has an average value of 0. It has a self-correlation, which usually I take to be a delta function. It is possible to take a self-correlation which is some function of time. So then I call it a colored noise. I have actually not managed to do anything with colored noise. Everything I say today will be with white noise.
Because lots of surfaces themselves have coloured noise shapes, don't they?
Yes.
Many of them. You have fractal. That's the same as different fractal dimensions.
Yes. So once the surface is formed, it will be colored in the sense that it will be a delta function. But in the way that I generate it, I only use white noise. But so.
And there are many surfaces that don't grow. So, for example, if you break something, make interesting so that doesn't fall into this class, does it?
There are surfaces that don't grow in the sense that I could imagine them as being the limiting end of these. So as time tends to infinity.
Oh, I see. So, okay, so it's not actually, this needn't be a physical model. It's just a way of mathematically generating.
Exactly,
surfaces.
yes. Sometimes it is a physical model when they hit equations, but it's not necessarily.
These all have steady states, or what are the asymptotics of the models?
That's a good question. In fact, for this surface, this is not even known whether this asymptotic state exists or not. So from a sort of more philosophical point of view, question is whether such classification is at all possible or not. For it to be possible, you need to have universality classes, because there are infinitely many rough surfaces, and bunches of them should classify into one class. Then the question is, can you do this classification right only at the end when you have reached the stationary state, or can you do it during the growth of time while it's growing? I don't have an answer to either of these questions. There are reasons to believe, there are mitigating circumstances that you can describe using renormalization group arguments and things like that, that the answer to both questions is yes, but they're by no means exact and clear. So I jump over those red questions. Now, to simplify my task, I am going to assume that the surfaces that I will deal with have a simple autocorrelation. That is, if you take the height difference, so by delta h here, I mean the height minus the mean. If you take the auto height correlation, it has a power law dependence. So this means that I don't have a scaling. I don't have a number setting the scale, which is good news in the sense that I am one step closer to conformal invariance. And it would have this behavior for distances which are shorter than some correlation length. As you drop atoms on a surface and the surface grows, there is some, right in the center where the atoms are arriving, correlations will build up. But far away towards the edge, there will be no correlation. And this correlation length will grow until over time it hits the boundary. So over large time, the correlation will be the same as the boundary of the sample in the lab.
So
And
X is now just a distance.
X is distance, yes.
Local distance.
So you look at two points on the surface, and you ask what is the correlation of height at these 2 points. It actually has two forms. It's if the distance between the 2 points is shorter than a given correlation length, then you have something like x to alpha. If it is larger, then you don't actually know what is happening. But the good news is that this correlation length grows with time. Also with
the length scale is what?
So I have no length. So no, I have no specific dimensional length scale. This is what I'm going to assume that happens, and it actually does happen with these 3 examples that I showed you. If there is a length scale, then I have a totally different game to play, and I don't want to get into that. And over a very long time, then correlation will stabilize into a constant value. And this is a sort of
what was that? The z, t to the 1 over z. What is
sorry. So I expect the correlation length to grow with time, like time to some power. And the power I denote as 1 over z, because this is a standard way of doing things. But people didn't write it as z, they wrote it as 1 over z. Because once you go back to your differential equation, it is given by the way the 2 sides of the equation scale with time and space. So the question is, if you scale space by some factor, how much time scaling do you need to compensate for that?
Is this alpha prescribed by you, or will it emerge from some equations?
No, it emerges out of the surface. So if you take the power spectrum of the surface, which is this expression below, alpha appears in the power spectrum. So if you shine light on a surface and measure the scattering of light, the power spectrum of this scattering will have alpha in it.
I know that, but in your theory that you're going to tell us, will alpha be put in or will it come out of the theory?
No, it will come out of the theory. So there are surfaces which have alpha equal to 0, and that means that you have in fact a logarithmic correlation, and then you have alpha equal to 1. Alpha is restricted to be, first of all, alpha has to be positive for it to be interesting, because otherwise I will just have a smooth surface. With alpha negative, things will just flatten out. I need alpha positive to be interesting. With alpha positive, now alpha has to be smaller than 1, because now I have a self-affine surface, in the sense that if I change the scale in the x direction, I can compensate for that, or change the scale in the y direction, or in the h direction, and the surface will look the same when you have that x to the alpha behavior. I want this change of scale in the height direction to be small enough so that at large distance I can see a surface. I don't want the height to grow way beyond so that it overwhelms the lateral distance. So alpha has to be smaller than 1. So this is a sort of summary of what I just told you. You can define a roughness for the surface, which is the square root of this self-correlation. The size of system is given by L, and as you start growing the surface will grow with some power of time until it reaches a saturation, and after that roughness will remain a constant. So for short times, roughness grows like some power of t to the beta, and for long times it's a constant value, L to the power alpha, and experimentally it has been observed that it has this scaling form, so that for t very small, alpha and z have to be related in such a way that you get the right asymptotic behavior, and that relation is just alpha divided by b. So by this way of characterizing surfaces, I just have two indices. The dynamical index, that is the rate at which it grows. Where is this pointer? So I have only two variables by this method of describing a surface, which are either alpha and z or alpha and beta to describe a surface. The third one will come out. So this is the standard problem of classification of rough surfaces. I will jump over these. Now, what I want to do is to add to these indices, or to somehow explain them, and that is, I'm going to do that by the Schramm-Loewner evolution. So the historical setting is that in critical statistical models, that would be something like Ising model, right at the critical point, boundaries separate the two different phases, and these boundaries are described by a process called the Schramm-Loewner evolution. And each Schramm-Loewner evolution is determined by a constant kappa, a positive real number, and which is referred to as the diffusivity constant. And this constant, the number kappa, sort of separates the universality class of the critical system. So for critical phenomena, the problem of universality is, as you know, solved, and kappa can somehow identify a whole class. So what are these critical domains? I've already mentioned Ising model, where you can set the spins up around some domain and down around another domain, and there is a wall separating them with the spins up and down on either side. This is what I mean. Or it can happen in the percolation problem, where I have set the sites as plus or minus on one side, and plus and minus on the other side, and a percolating path has to find its way going from A to B. So this is also a Schramm-Loewner evolution with a different kappa. It can also be used to describe not necessarily a critical path, but something like a self-avoiding walk. So you have a random walk in 2 dimensions. It randomly chooses to float around, but it does have the condition that it should not cross itself. So it's a self-avoiding walk. All these are different classes of the Schramm-Loewner evolution. But what is it? Loewner suggested that if you have a path on the complex plane, which would be something such as this trace here, you can, instead of giving an equation for its evolution, you can give a conformal mapping which maps the upper half plane to itself, but at this takes this path and embeds it into the real axis. Well, it's a difficult way of describing a path, but the good thing is that it is the conformal mapping which does this satisfies a simple differential equation, which is that. And I think this is the contribution of Loewner, that this path would satisfy such a simple looking equation. So if you take the map GT of Z, you can see that for short times it has to behave like that, because at t equals to 0 it has to be Z. It's just the identity map. And as time grows, it will have components added to it, and it has a Laurent expansion because it's an analytic map. So the first term which appears here is a 1 over Z. And in fact, I have a freedom to set this number 2 here, which is related to this number which appears here, which you can see that by rescaling time I can absorb this number. This number is referred to as the capacity.
I ask, so
And
this
yes,
requires a regularity, so it's not true for every arc. The arc has to be a quasi-arc. I mean, the existence of a conformal map, you can't send an arbitrary curve to the real axis by a conformal map.
no. So this does restrict the arc into or the trace of the SLE into certain things. Not everything is possible. For instance, it cannot be self-crossing.
But there's differentiability conditions which worry me because you're dealing with highly non-differentiable arcs here. And it has to be a quasi-arc, so there's a whole huge theory of these things. Anyway, but carry on. But I did want to say that...
Okay, I'm not familiar with that, but I can see that what you're worried about is that these will be very, very, very irregular paths, but but I have controls over them. They are not any old irregular path. And A of t is called the driving function because once you have Loewner's equation here, you give me a function of time, then I can solve that, and that gives me a path in the upper half plane. The next contribution comes almost 80 years later, where Schramm suggested that if you put in for the driving function a Brownian motion, and here is the sort of the variance of the Brownian motion. So if you take this with variance 1, I control the variance with kappa. Then you get paths in the upper half plane by solving the Loewner evolution, which are then stochastic. They are random paths, random non-self-crossing paths. But this is what Schramm did. He showed that they have a conformally invariant distribution. That means that if you take any analytic mapping of the Z upper half Z plane to itself, the distribution remains invariant. So by this method, I have paths generated. So remember that I have a complex, I have a random path put in, and this random path will look something like this. The tip of it is here, although this is not a very convincing picture. That this path starts here, comes down, and then goes up again. The very tip of it is here. So if you fix t, it goes only so far into the upper half plane. Then there is a mapping from upper half plane to itself, which completely absorbs this into the x-axis. It's very nice to get rid of this monster so easily. And only thing that is left of it is this A of t. This random path excludes a part of the upper half plane, which you can see here. So if I paint it yellow, yellow won't go into certain parts because it is protected by this part. I call that the hull. So in fact, it is the upper half plane minus the hull of this part, which is going into the upper half plane.
So the white part, the hull, that goes into the lower half plane or somewhere else?
The axis doesn't.
No, it goes into the axis.
All of it?
All of it goes into the axis.
Not-
It is a little unnerving. I agree with you. It gives you a strange feeling that a two-dimensional entity is squashed into a one-dimensional entity.
But not by a conformal map. No, the hull just disappears. It's not in the domain.
Right, and the conformality's on the interior anyway.
I mean,
Yeah.
it's just a Riemann mapping theory. You can
Right.
Yeah.
do the upper thing is simply connected, so you map it there. It extends to the boundary if the boundary is regular to there. But the rest of the stuff just goes away.
But I can take a point in that hull and apply the mapping G, can't I, to see where it goes? It'll give you something.
No, it's not
No,
quite
it doesn't get mapped anyway.
No, I think the comment is correct.
G
that
has a natural boundary.
The analytic mapping only exists in the outside of the hull. It's in that domain that it is. Once you get out of it, it is not regular anymore.
So where does the other endpoint of the green curve go? Is it fixed under the mapping? Is that the boundary condition?
So I have 2 points. I have the starting point and the end. The starting point also goes somewhere, which I haven't pointed out on this graph, and I don't know. I can't answer your question now.
There's some normalization of the conformal
yes.
map. In those,
Yes, it is. You can work out where it goes. It's. So a simple example. Take a very simple curve in the upper half plane. So a point zeta goes to zeta plus IA. And there is a conformal mapping which just takes this slit and embeds it into the real axis. And what is that mapping? It's just that. So if you look at this map, you see that the point z equal to zeta plus IA goes into zeta. If I take A to be related to my time variable by that formula, I can look at other properties of this map. I can differentiate it, and you see that it satisfies the Schramm-Loewner evolution. And at t equals to 0, so if I set t equals to 0, it is the identity map. I can expand it for large z, and it does have that form. So it's I will call this a slit map. I'll use this a lot, and this is the simplest example of a solution to the SLE equation. So here are the postulates which govern SLE. This is shown by Schramm, that if you use a Brownian motion as the driving function, you have two properties. One is that the path is domain Markov. So if you take a domain and 2 points on the edge of the domain are connected by a trace, then you cut this trace at some midpoint. You can construct a map, a combined map, which takes part of it into the boundary of the domain, and the other part will still remain SLE. And the other property is conformal invariance. So if you take any mapping of this domain into itself, points change, the shape of the domain change, but the probability distribution of the paths don't change. So here is the domain Markov property explained again. So I can take a percolation path and cut it somewhere in the middle, and divide this process into two processes, from R1 to Tor, and then from Tor to R2, and I can find a conformal mapping which takes this into the boundary, so that I will have just gamma 2, and then the conformal property helps here because the property distribution then does not change, and I have the Markov property. And this is the expression of the conformal invariance. That is, you have this situation, and you take an analytic mapping of this domain to itself, and R1 and R2 change, but I still have the same total probability of these paths. So you can take this Loewner evolution, stick in the various driving functions, and you get nice shapes. The non-crossing property sort of shows itself. You get paths which do not cross themselves. You can now put in Brownian motions and then computer generate paths. You see that as kappa increases, you get increasingly more complex fractal shapes. What is important is to note that I actually don't have a hull for these two, but I have a hull for this curve, and I'll argue in a moment that for kappa bigger than 4, you do get a hull. For kappa smaller than 4, you don't get a hull, because kappa equal to 4 is a transition point. After that point, this path can touch itself. It won't cross, but it can come and touch itself and go away again, and that way it separates certain parts of the upper half plane. So you get paths like that for kappa between 0 and 4, and you get a path which touches itself and creates a hull for kappa between 4 and 8. At kappa bigger than 8, you get a space filling path. It is consistent with a fractal dimension which I can define for these paths, which is 1 plus kappa over 8. So for kappa bigger than 8, this fractal dimension is 2. So I don't really have an interesting path for kappa bigger than 8. This defines my domain of interest. There is a connection with conformal field theory, but I don't want to go into that. And the way the connection is constructed is that you look at the Fokker-Planck equation governing the distribution of these paths, and that can be written in terms of operators of conformal field theory, and then you identify this as a null vector level 2. And once you do that, the central charge of a conformal algebra will be given in terms of kappa, which if I write it like that, you see that it has an obvious symmetry or duality. By changing kappa to kappa prime, provided you observe that, this central charge doesn't change. So it suggests that there is the duality, and in the next slide I explain what the duality is, and you can show that the fractal dimension is related to some operator in conformal theory, which gives you this fractal dimension 1 plus kappa over 8. So I can explain what the duality means. So suppose I have a SLE trace, and I put it into some software, such as the Paint software of Microsoft, and I fill in the left-hand side with color yellow. The color yellow is not going to spread everywhere. It is going to be restricted by this path, and it will certainly not go into the hull. The hull will be left out. So an outside trace will be given, which is this trace here, and this is another fractal path. And you can show, or the grant here show, that these two are in fact the two SLEs which are dual to each other by the formula which I showed you on the last slide. So if this has kappa, this trace will have kappa prime. And naturally, if this has kappa bigger than 4, that will have kappa smaller than 4, and therefore no Hall. And this is the duality which exists between them, and hence, if kappa can at most be 8, it can at least be 2. So it restricts my domain of attention between kappa equal to 2 to kappa equal to 8, and it has a midpoint at 4 where the behavior changes.
So each of these paths are always defined by just a single fractal dimension?
Yes. Yes, it is a single fractal. No. Are you referring to multifractality? No, then there is no multifractal. There is an open question here, and that is if you recall, I talked about this partial differential equation which governs the PDF. The only way I can attack this problem from this point onwards is by invoking conformal field theory. There has to be, in the theory of partial differential equations, independent of conformal field theory, a way of deriving these results. I have not seen that done. So it is very strange. I cannot see how you can use partial differential equation which theory to put limits on the values of kappa and the possible solutions. So that is there is an open problem there. So what do you then do with it? You can relate various calculations. This was a calculation done by Cardy, where he asked what is the chance of a percolating path if you have 4 distinct points on the edge, on the boundary of a domain, for a path to emerge out of one sector and exit through the other sector. You can relate that, since percolation is an SLE of kappa equal to 6. You can relate that to some question in the SLE problem. That means that is an SLE which exists out of a sector on the real axis and touches the real axis on another sector, and these two probabilities equal, and you can do these kind of calculations. So this ends my review of SLE, and I have little time to say how I'm going to use it. So can I use it to classify rough surfaces? I have to take a jump here, a sort of jump that physicists are allowed to take, but mathematicians are not. I don't have a proof. I just have a feeling that this can be done. So the way I do it is that I take a rough surface and use what the cartographers do. Look at equal height surfaces. Equal height lines on a given domain would look something like this. Now, if the surface is a rough surface, these will be fractals. They won't be smooth paths. And I claim that they are SLE. So take a random surface, h of x and y, find the isoheight lines, and then that gives you a soup of loops like that, which we used to have when we were kids. These pasta loops were made into soups. And these are now fractals, and I want to analyze them and classify them. But these are loops. My SLE theory needs paths, traces. So I cut them somewhere. Take a line and cut one of these loops, and you have 2 points A and B, then use a conformal mapping, send one of them to infinity. There you have now a trace in the upper half plane, and test if that is an SLE. So that would be the kind of trace you find after you take a loop on a rough surface, and then you test whether it is SLE. How you do that is by a numerical method. So I actually used my slit map, the slit map that I talked to you about, and try and approximate this path by successive applications of that slit map. So this is how it is done. You have to, at time 0, you have a path which goes to Z1, Z2, and Z3. Then you use the slit map, you take Z1 in. Z1 goes in, then there will be Z2 and Z3, then apply it again, Z3 is left, and apply it again. And in this way, step by step, the path is absorbed. And then take something like the rough surface I showed you, the deposition of tungsten oxide on glass. Its isoheight surfaces look like that. And then apply to the isoheight surfaces of that. There is the problem of where I cut. So you taking all of the isoheight surfaces is going to be a daunting process. And you have to take only a collection taken at a certain height. So what happens if I change the height? You can see that things are not invariant as you change the height. This is a numerical experiment. The number of, if you cut at a certain height, you get lots of lakes. And the masses of these lakes is the number of, or the mass of the lake, I should say, it grows, drops with some power torr, but torr is sensitive to where you cut. And it seems that if you cut above the mean line, mean height, you are safe. So that is where we stand. We go just above the mean height, and then it's a numerical process, and you test to see if you have an SLE. There are 3 different tests you can perform. One is that you directly apply the slit map and see if the driving function you get is a Brownian motion. The other one is that you calculate the passage to the left of a point. So this path comes and you have a reference point and you ask what is the probability that it passes through the left of this point. And then you can also look at the winding angle. The path moves up and down, and the tangent to it is an angle which would have a random distribution, and it has a random distribution which is related to kappa. Good thing is that we have formulae for all these. So the probability of passage to the left was calculated by Schramm, and it is this hypergeometric function. You test if this holds in your numerical calculation. And the winding angle should have a variance which is related to kappa and the size of the sample. So if you go distance L away, the distribution of theta squared behaves with logarithm of L. You can test for these numerically. So take an example. This is example looks for SLE curves in 2D turbulence. So if you have 2-dimensional turbulence, this is computer simulated, and you look at the vorticity positive areas and you color them. So all the colors are vorticity positive areas. And where you have vorticity negative areas, you color it black. So it's somewhere like that. The path between positive and negative vorticity area, that is a vorticity 0 path, is some fractal. So if you can pull that fractal out and apply the SLE test, and you find convincing numerical evidence that it's actually it's behaving over time almost linearly, has the right Gaussian distribution, and that is believed to be an SLE. We can do it for the Cardan-Parisi-Zhang equation, and that comes to be related to SLE 8/3, which is in fact the SLE of the self-avoiding random walk. So this is the Cardan-Parisi-Zhang equation, various symmetries. By the way, these are known for KPZ. If you take KPZ equation in one dimension, not my interest, but it has an exact solution, and you can calculate alpha and beta for it, the exponents of roughness. When 2 dimensions, the exponents are not known. These are good approximations worked out by numerical calculation, and we find the same. So for kappa equals to 8/3, you can derive alpha and beta for it, and that comes out right. There are other models which are believed to be in the same universality class as KPZ. This is what I mentioned, that there are reasons to think that universality classes exist. So the Eden model, the ballistic deposition model, and the restricted solid model all are believed to be in the same universality class as KPZ. They're different rough surfaces, but when you do this test, they do fall into the same class. They do have different intercepts, which I still don't understand why they should have different intercepts in this graph. But they have the same slope. And we did this for the tungsten oxide surface. You can in fact do it for any surface. The tungsten oxide was chosen because experimentalists in my lab, in my department, have studied it a lot. We knew it has self-affine form, so everything was ready, and the sample was cheap and easy to get. No physical reasons for choosing this material, and that also has relatively good behavior. It's not a completely straight line, but these are, I think, are computational errors that a better numerical analysis would reduce. So the error is a very large error on this determination of kappa. Finally, explosive percolation. I take a little bit longer to tell you about this explosive percolation. What I have jumped over is that I actually suggested to Professor Kida that the turbulence could perhaps be done by his flakes, that this computer simulation could be replaced with an actual experimental observation. Somehow put the flakes into a fluid, make it turbulent, and find the zero vorticity lines. That's all I can say. I don't really know how to do it, but it's worth thinking about. Now, explosive percolation is a story which percolation is a continuous phase transition, and it is always considered strange that it is a continuous phase transition, and people have tried to make it discontinuous, to make it into a first order transition. It is obvious that by no local rule can you make percolation into a first order transition. So people have used non-local rules. The non-local rule goes like this, that you have 2 clusters, so pink and yellow here, and there is a bond that connects them. This bond, so we are talking about bond percolation here, is connected in competition to another bond which also connects two clusters, depending on a rule. The rule could be the product rule, which means that you multiply the number of elements here, the number of elements, and whichever is smaller, that one gets connected, or the sum rule. You add them. So this, you can see, this is a highly non-local rule, and it was claimed by these people, Science 2009, that if you take the product rule, it makes percolation discontinuous. This is graph taken from the paper. You can see there's a very sharp transition. However, it turned out that they were wrong, and it still remains continuous. So these guys showed that it remains a continuous percolation. This kind of percolation is called explosive, because your rule actually inhibits the largest cluster from growing, but there is an extent to which it can do it. And after a certain point it fails, and this largest cluster suddenly explodes and connects the two ends of the sample. These guys then showed that this connection, this product rule, it makes the edges of the largest cluster a fractal, which is in fact a watershed, and the fractal dimension of the watershed appears in both theories. Now, as question is, are watersheds SLE? So we can apply our method to the watersheds or explosive clusters, and the answer is yes. It is a with very good numerical accuracy. These guys in Zurich have very much better computers than we have.
How do you define a watershed?
Now, watershed has the word watershed has an American and English definition. In the English definition, watershed is the line which delimitates the catchment area of a basin.
Yeah. So how do you define that in this case?
So it's actually a line which goes from summits to saddle points, etc. So
it's defined by Maxwell in 1860 something.
yes.
Exactly.
Yes. So, or algorithmically, you can fill up your rough surface with water, and this water will form a growing lake until at some point it pours over, and that is the watershed.
So my question was, how can you apply that notion when you don't have a smooth surface?
Well, you actually use this algorithm of filling it with water. So you use invasive percolation method.
That works even if you don't define summits and.
Yes.
Yeah, okay. Good. Saddles. Yeah.
Yes.
Good. Good.
So that is how the watershed is defined in this method, in this paper. You use an invasive percolation algorithm, and you find the delimiting line, and the delimiting line is a fractal. Then you test whether that fractal is an SLE, and the answer is yes. However, kappa falls outside my range. Kappa was not supposed to be smaller than 2. Here I have a kappa which is 1.73. Very much like the square root of 3, but I don't know if that's true. Having this kappa means that my connection with conformal field theory will go under question. In fact, conformal field theory is supposed to have central charges which are positive. I have a negative central charge here. So there is a dilemma. This paper is published now. It came out last week. So I'm thinking whether I can relate that to logarithmic conformal field theories which have negative central charge. So I left you with this table, which gives you kappa, central charge, fractal dimension for various models. And these are the red ones are the models which I mentioned, I didn't actually tell you the details of the abelian sample model, but that's just another exercise. And these are the models which have been studied. Most of them you see are critical models. But these guys are rough surfaces, these four. So kappa ranges, my table used to end here. So 2 to 8, and in fact at 8 you do get a negative central charge, but that is kind of understood. People don't object to that so much. Just that there is a well-known conformal field theory related to -2. And conformal dimension, the fractal dimension of this SLEs grows right up to 2. Thank you very much for your attention.
Yes.
So we all have some intuition about fractal dimension, but what's the intuition I should have about kappa? And more specifically, is there, for example, for the situation that you described in turbulence, suppose I get some kappa. What information about the physics, if any, do I get?
It's a good question. I didn't I didn't explain this. I can derive a relationship between alpha and kappa. Alpha was the roughness exponent. I can give alpha in terms of kappa, provided I am in a situation where I can make sure that the distribution is Gaussian. That is, I have H2 minus H symmetry. If that symmetry doesn't exist, then I don't have a specific relation between alpha and kappa. So in that sense, once you have kappa, you can say what kind of roughness you are dealing with. I hope in future to be able to get other relations as well, that kappa should give you the various roughness exponents, so that alpha is only the second order one, the higher order. If it is Gaussian, you only have alpha, but if it is non-Gaussian, you will have other exponents describing the surface. So kappa is a classifying number. It classifies the roughness. Not much use.
Turbulence is a rather curious, 2D turbulence is a curious application of this theory, because if it's freely decaying, even if it starts off with that very fractal appearance, it resolves itself very quickly. And the inverse cascade means that it smooths itself out. So if you let it evolve for a little while, it won't be fractal anymore. In fact, it ends up in a box with just 2 large eddies. That's the feature, the best known feature of 2D turbulence. It's a different matter if you force it. But then if you force it, you'd expect to be, it depends on the forcing, you know.
The forcing will have an effect, yes. Yes, I don't know what to say about that.
It would be interesting to study the evolution towards the smoothness.
Yes, it would.
One could
Yes,
do
indeed.
this.
That's true. And the region of fractality then moves gradually to, I mean, it'd be nice to relate this to the spectrum.
Yes, the relation to spectrum now, I slided over it, is problematic. The point is that you shine light on a rough surface, and you get a reflection, and you study the power spectrum here. The mathematical expression assumes that you have actually reached all the points of the surface, because that's a Fourier transform. However, there are shadows. As you shine light, some peaks will make shadows, and certain parts of the surface will be left out. And if it's a rough surface, that's not a small part of the surface, it's a very large part. So the problem of actually connecting an observed power spectrum to the roughness is...
But pure theory, can you do it?
in pure theory you can. Yes.
and relate
Yeah.
these coefficients to spectral exponents.
Yes.
Yeah, right.
So the fractal, let's go all the way to the left column. The fractal dimension of the watershed boundary is this 1.1. But what about the surface itself? And I guess as we've talked about the contours in that the fractal dimension of the rough surface is.
No, no. This is so. I'm saying that. Okay, good question. This experiment, numerical experiment, was done for a random surface. That is a surface which has alpha equal to 0. It has so it's if you have non-zero alpha, then all these numbers will probably change. We don't know how they will change. This so you take a random surface, that would be a Edward Wilkinson surface. Fill it up with water, find its watershed, and the watershed in the kappa is 1.72. You are right. We should really repeat the experiment for the whole range of different surfaces and look at their watersheds to see how watershed changes with the roughness exponent.
So I would like to take a message home, so to speak. So your idea about relating the surface roughness as we understand it commonly,
Yeah.
What you feel when you touch, is to study this property of level curves.
Yes. To study the property of the level curves in the sense that
By these methods.
that level curves are fractals. Yes. A correction. I have to add here that I have really restricted myself to a very special set of surfaces, natural surfaces, which you have here,
Yeah.
have a scale. There is a scale to it, and I have omitted all the scale. So if you look at a scale-free surface, then you can use this one.
So this is complementary to the fractal dimension of the surface, or the multifractal cascade of dimensions if it's more complicated.
Yes, yes, yes. That's true.
Because that fractal dimension provides a very natural, immediately, when you get used to looking at different fractals, gets a very immediate characterization of the nature of the surface, even though it's not everything, as you say.
Yes, yes.
But Mandelbrot has other, for example, lacunarity. There are different related quantities.
Yes.
Does it fit into this story?
Yes, I'm actually currently involved with that to relate all these together. Yes. So there are different definitions of fractal dimension, and they somehow connect up with this watershed. I don't. That's work in progress. I don't have anything to say now.
Oh, this is really very nice in the way it somehow unifies the theory of random surfaces in so many different contexts. That's what I find interesting.
Yes.
So anyway, we just need to know the K.
But also, if anyone is an expert on partial differential equations, these numbers should be explainable in terms of partial differential equations.
Yeah.
I have never seen anything like that. That partial differential equation can tell you something about the coefficients or the parameters which go into the coefficients.
Well, it's an eigenvalue problem, is it not?
It's a very fixed eigenvalue. You're looking for zero eigenvalue, but the existence of a zero eigenfunction, I think that's is conditional on certain values of the parameters.
K to the minus 5/3 should be explained in terms of the Lilly
Yes, for
equation,
example.
but it isn't.
Yes, that's an example.
It's a well.
Okay, well, with that thought, let's thank you again.
Thank you very much.